Title of the module: Trees. Today we are going to learn about a special class of graphs called trees. The word tree suggests branching out from a root and never completing a cycle. In 1847, Kirchhoff developed the theory of trees in order to solve the system of simultaneous linear equations. In 1857, Cayley discovered the concept of trees by considering the changes of variables in the differential calculus. Trees have many applications, especially in data storage, communication and searching. Definition: a graph that contains no cycles is called an acyclic graph. An acyclic graph is called a forest. A connected acyclic graph is called a tree. So, a tree is a forest and every component of a forest is a tree. Example: paths are trees. A tree is a path if and only if its maximum degree is 2. A star graph is also a tree. Now, let us see some more examples of trees as well as a non-tree. Consider the figures shown on the screen. The graph A, B and E are trees. The graph C and D are not trees. In the figures shown on the screen, the graphs A, B and E are trees, whereas the graphs C and D are not trees because C contains a cycle and D is disconnected. Hence, they are not trees. In the figures shown on the screen, all are trees on 6 vertices. Trees have many equivalent characterizations, any of which could be taken as the definition. Let us see the first theorem. Let G be a graph with n vertices and m edges. Then the following statements are equivalent. G is a tree. Every 2 vertices of G are joined by a unique path. G is connected and n is equal to m plus 1. G is acyclic and n is equal to m plus 1. All the 4 statements are equivalent. First, we shall prove that 1 implies 2. Let G be a tree. Let U and V be any 2 vertices of G. Since G is a tree, G is connected and acyclic. Hence, there exists a UV path in G. We have to prove that there exists a unique UV path. Suppose not. There exist 2 distinct UV paths, namely P is equal to U0, U1, U2, so on up to US is equal to V, and another path Q, U is equal to V0, V1, V2, so on up to Vt is equal to V. Since P and Q are distinct, there exists at least a positive integer I such that 1 less than or equal to I less than or equal to T and Vi does not belong to the path P. Hence, Vi minus 1 belongs to P intersection Q. Let J be the least positive integer such that I less than J less than or equal to T and Vj belongs to P. Now, the Vi minus 1 Vj path along Q followed by the Vj Vi minus 1 path along P form a cycle, which is a contradiction. Therefore, there exists a unique UV path in G. Hence, every 2 vertices of G are joined by a unique path since U and V are arbitrary. Next, we shall prove that 2 implies 3. Suppose that every 2 vertices of G are joined by a unique path. To prove that G is connected and n is equal to m plus 1. Since any 2 vertices of G are joined by a unique path, G is connected. To prove that n is equal to m plus 1, we shall prove this by induction on n. The result is obvious for connected graphs on 1 and 2 vertices. Assume that the result is true for graphs on at most n minus 1 vertices. Let G be a graph on n vertices and let x is equal to uv belong to the edge set of G. Since there exists a unique UV path in G, G minus x is a disconnected graph having exactly 2 components say G1 and G2. Let G1 be a graph with n1 vertices and m1 edges, and G2 be a graph with n2 vertices and m2 edges. Then n1 plus n2 equals n and m1 plus m2 equals m minus 1. Let this be equation number 1. Now, by induction hypothesis, n1 is equal to m1 plus 1 and n2 is equal to m2 plus 1. Therefore, n is equal to n1 plus n2, which implies that n is equal to m1 plus 1 plus m2 plus 1. This implies that n is equal to m1 plus m2 plus 2, which in turn implies that n is equal to m minus 1 plus 2, using equation 1. Hence, n is equal to m plus 1. Therefore, G is connected and n is equal to m plus 1. Now, we shall prove that 3 implies 4. Suppose G is connected and n is equal to m plus 1. To prove that G is acyclic and n is equal to m plus 1, it is enough to prove that G is acyclic. Suppose G contains a cycle of length k. We are going by proof by contradiction. Then the cycle contains k vertices and k edges. Consider a vertex V among the n minus k vertices not on the cycle. Since G is connected, we can find a shortest UV path in G. Consider the edge on the shortest path incident to V. The n minus k edges thus obtained are all distinct. Hence, m is greater than or equal to n minus k plus k, which is equal to n, which is a contradiction to n is equal to m plus 1. Therefore, G is acyclic. Hence, G is acyclic and n is equal to m plus 1. Now, we shall prove that 4 implies 1. Assume that G is acyclic and n is equal to m plus 1. To prove that G is a tree, it is enough to prove that G is connected. Suppose that G is not connected, then G has more than one component, namely G1, G2 and so on up to Gr, where R is greater than or equal to 2. Each of these components Gi, where 1 less than or equal to I less than or equal to R is a tree, since G is acyclic. Then Ni is equal to Mi plus 1, where Gi is a graph with Ni vertices and Mi edges. Hence, the summation I is equal to 1 to R Ni equals summation I equal to 1 to R Mi plus 1, which in turn is equal to summation I equal to 1 to R Mi plus R. This is equal to n equal to m plus R, where R is greater than or equal to 2, which is a contradiction. Therefore, G is connected and hence G is a tree. Next, let us see an immediate corollary of the above theorem. Corollary 1. Every non-trivial tree has at least 2 vertices of degree 1. The proof: since G is non-trivial, the degree of V is greater than or equal to 1 for all vertices V. We know that the summation degree of V is equal to 2m, which is equal to twice n minus 1, that is equal to 2n minus 2. Hence, the degree of V is equal to 1 for at least 2 vertices. Theorem 2. The origin and terminus of a longest path in a tree have degree 1. The proof: let G be a tree. Let the longest path of G be the path P u equal to V0, V1, V2 so on up to Vs, which is equal to V. Suppose that the origin u has degree greater than or equal to 2. Then u must be incident with at least one vertex, say W, other than V1. Now, the WU line followed by the path P is the longer than the path P, which is a contradiction. Hence, the origin has degree 1. Similarly, we can prove that the terminus also has degree 1. Now, let us see some problems on trees. The first problem: let the degrees of the vertices of a certain tree T of order 13 be 1, 2 and 5. If T has exactly 3 vertices of degree 2, then how many n vertices does it have? Now, we all know the structure of a tree, and this tree is said to be of order 13, which means that it has 13 vertices, and all the vertices of this tree T have degree 1, 2 and 5. We know that the n vertices of a tree have degree 1, and you are given one more clue that T has exactly 3 vertices of degree 2. You are asked to calculate how many n vertices does it have. Given this problem, I am going to give you 15 seconds to ponder over this problem. You have been given 15 seconds to ponder over the problem. I am sure you have arrived at the right solution to this problem. Let us now see the solution. So, the solution is that given that you have 3 vertices of degree 2 and the order of the tree is 13, the remaining 10 vertices are of degree 1 or 5. You can look at the problem. There is 1, 2 and 5 as degrees, 13 vertices. There are 3 vertices of degree 2, and therefore, if you are going to subtract those 3 vertices from the total number of vertices, it means that the remaining vertices have degree either 1 or 5. So, 3 vertices of degree 2, if you are subtracting those vertices from 13, the remaining 10 vertices are of degree 1 or 5. So, x be the number of n vertices of T. This is what we have to calculate. X is required, and T has 10 minus x vertices of degree 5. So, the remaining vertices have degree 1 or 5 means the vertices with degree 1 are obviously the end vertices. So, the remaining vertices, namely 10 minus x vertices have degree 5. Therefore, since the order of the tree is 13, this implies that the size of the graph is 12. What do you mean by size of the graph? It is the total number of edges. Therefore, 1 times x plus 2 times 3 plus 5 times 10 minus x. So, 1 is the degree of x vertices, 2 is the degree of 3 vertices, 5 is the degree of 10 minus x vertices, and together it is equal to 2 times 12. This is by the fundamental theorem of graph theory, that is, the sum of the degrees of the vertices is twice the number of edges. So, using this, I have written this statement. By solving this for x, this algebraic expression for x, you get x is equal to 8. So, x is the number of vertices with degree 1, or in other words, they are the end vertices, and therefore, the tree T has exactly 8 end vertices. The next problem is, show that every tree with average degree k has 2 by 2 minus k vertices. So, this is what we have to prove. It is a proving type problem. So, T has n vertices and m edges obviously, then n is equal to m plus 1. This is by a theorem that we studied, the equivalence conditions that we studied. Therefore, we already know that for a tree n is equal to m plus 1. And the average degree is a total degree sum divided by n, that is k is equal to summation of the degrees of the tree divided by the total number of vertices n, that is equal to 2m by n, that is equal to 2 times n minus 1 by n. This n minus 1 comes from here. So, m is equal to n minus 1. So, I am substituting that here. And using this, we are going to solve k n is equal to 2n minus 2, and 2n minus k n is equal to 2, and n into 2 minus k is equal to 2, and therefore, n is equal to 2 by 2 minus k. Thereby, we have proved that every tree with average degree k has 2 by 2 minus k vertices. Now, we shall see the definition of the distance between two vertices. If G has a uv path, then the distance from u to v, denoted as d of u comma v, is the length of the shortest uv path. The definition of the center of a tree. Let v be a vertex in a connected graph G. The eccentricity E of v of the vertex v is defined by E of v is equal to the maximum of all distances, that is maximum of all d of u comma v such that u belongs to vertex set of G. The radius r of G is defined as r of G is equal to the minimum of all eccentricities, that is minimum of all E of V such that V belongs to V of G. The diameter of G is the maximum eccentricity of G. The vertex V is called a central vertex if E of V is equal to R of G and a set of all central vertices is called the center of G. Now, we shall see a theorem based on the center of a graph. Every tree has a center consisting of either K1 or K2. So, we know that K1 is a vertex and K2 is an edge. And the proof, before seeing the proof, let us consider an example now. Think of a tree or a path with 4 vertices and also a path with 3 vertices. Can you think of the center of these two graphs? The path with 4 vertices as well as the path with 3 vertices are both trees. So, you need to find the center of the graph. I am going to give you 15 seconds to ponder over this. The 15 seconds are now over. I am sure that most of you must have arrived at the right answer. For the path P3, the center of the graph is K1, and for the path P4, the center of the graph is K2. You must have calculated this using the eccentricities of the graph. Now, let us go on to the theorem. So, every tree has a center consisting of either K1 or K2. So, that is the theorem we are looking for, and the proof is assume that T has at least 3 vertices. Why? Because when you have only one vertex or 2 vertex, it is automatically K1 or K2, thereby it is a trivial case, and therefore, we are jumping over to a tree T with at least 3 vertices. And now, T has at least 2 end vertices and let U belong to the vertex set of G. Clearly, the maximum of all the degrees U comma V occurs only if V is the end vertex. This is quite obvious. When you see the eccentricities of the graph, when you see the maximum distance of any vertex U and V, it will happen only when U and V are at ends of each other. So, the maximum distance is when they are endpoints. Therefore, this statement is quite true. Now, delete all the end vertices of the tree T. You are arriving at a new tree, namely T dash. The resulting graph T dash is also a tree, and the eccentricity of this graph is exactly 1 less than the eccentricity of the previous graph. Therefore, E of V, where the vertex V belongs to T dash, is equal to E of V minus 1, where V belongs to the original tree T. Now, the minimum of all eccentricities is equal to the minimum of all eccentricities in this graph. So, T dash and T, the eccentricities do not change, the minimum does not change. So, from this you can conclude that T and T dash have the same center, and by repeating the process n number of times, we arrive at either K1 or K2. Since the tree has only a finite number of vertices, by repeating the process so many number of times, finite number of times, we arrive at K1 or K2. Hence, the proof of the theorem. If you remember the question that I posed at the beginning of this theorem, I asked you to find the path P4 and path P3. I asked you to find the center of these two trees, and you had arrived at either K1 or K2 as the solution. So, it is in keeping with this theorem, and also that you can remove the end vertices. That is the technique that we have outlined in this theorem. You can remove the end vertices and arrive at the center of the graph. So, by removing the vertices recursively continuously, you are arriving at either a single vertex or a vertex or an edge K2. So, K1 or K2. So, even for path P4, if you remove the last 2 end vertices, you are arriving at K2, and for the path P3, if you remove the last 2 end vertices, you arrive at a single vertex, namely K1. So, this is also another way of looking at things. Let us now see an example to understand the theorems and definitions that we have studied just now. We now have a tree with 21 vertices. It is a tree because there are no cycles, it is a cyclic graph, and 21 vertices are there. The numbers marked in black are the eccentricities of the vertices, and clearly you can see that the end vertices are having maximum eccentricity in keeping with what we have studied earlier. And so V3, V1, V21, V20, V9, V10, all these are end vertices, and all of them have the maximum eccentricity, which is 7. The other vertices, of course, you calculate the maximum distances and you write the eccentricities close to that vertex. And for the vertex V1, it is V21 is the longest path. So 1, 2, 3, 4, 5, 6 and 7. So which is why V1 has eccentricity 7. Likewise for V21, if you are going to look at the longest path, it is V1 to V21. Therefore, V21 also has the eccentricity as 7. We already saw that the center of a tree is those which the minimum eccentricities, and here it is K2. Why? Because both V12 and V13 have the minimum eccentricities, namely 4. The rest of them have bigger eccentricities, and therefore these two vertices have minimum eccentricity 4, and the subgraph induced by these two vertices is an edge, namely K2, and this is in keeping with the theorem we studied that the center of a tree is either K1 or K2. At the end of this session, we have studied about the concept of trees, its definition, some of the theorems related to trees, its properties. We even solved some problems in trees. I hope that this session was useful to you. Try to create many more examples and learn about the properties of trees, and also try to do the quiz and the assignment in this module, because we learn by doing. Thank you.